Hello, this is Richard Hammack's Calculus 1 course. We are in part 4 of the course on applications of differentiation. Today in lecture 36 we'll talk about two related topics called linear approximation and differentials. We'll begin with linear approximation. This is not something that you'll use often, but it's a very enriching and helpful point of view. It gets to the central idea of calculus, that up close, nonlinear functions look linear. To explain it, we'll start with a problem that we've seen many times. Find the equation of the tangent line to the graph of y equals f of x at a particular point a f of a. So here's the picture. We have a function y equals f of x. We pick an x value of a and look at the corresponding point a f of a on the graph. And there's a tangent line to the graph at that point, shown red here. And we're looking for the equation of that tangent line. To find it, we could use the point-slope formula for the equation of a straight line. Y minus y naught equals m times x minus x naught, where x naught, y naught is a point on the line, and m is its slope. The point that we know on the line is a f of a, and the slope of the line, as we know, is f prime of a. So putting that information into the point-slope formula gives y minus f of a equals f prime of a times x minus a. Now solving for y by adding an f of a to both sides gives us the equation of the tangent line. Y equals f of a plus f prime of a times x minus a. This is a linear function. You could get it into the form of y equals mx plus b, but we're going to leave it in this form for convenience. Since it's a linear function, let's give it a name. Let's call it L of x. The equation of this tangent line is y equals L of x, which is f of a plus f prime of a times x minus a. So we have two functions here, our function L of x, which is nonlinear, and then a linear function, y equals L of x, given by this formula. It's important to note here that when you're looking at the situation close to the point a f of a, you can barely tell the functions L of x and f of x apart. They pretty much overlap. They're almost indistinguishable. If you took an x value that's close to a, like this one, and you compute L of x to get a point on that tangent line, it's almost the same as f of x. They're very, very close. You would say that f of x is approximately equal to L of x for values of x that are near a. Summarizing this, we get what we call the linear approximation formula, that f of x is approximately equal to L of x, which is f of a plus f prime of a times x minus a, whenever x is near a. They're not quite equal, but this nonlinear function is approximately equal to this linear function. That's called the linear approximation formula. And this linear function, we're denoting it as L of x. L of x is f of a plus f prime of a times x minus a. And this function, L of x, is called the linear approximation to f of x at a. The way to think about it is that L of x is the best fit to f of x by a linear function at a. The graph of y equals f of x, the function f of x, is nonlinear. It might be quite complicated and complex, but up close to a, it has this almost perfect fit by a simple linear function. That's the linear approximation to the complex function f of x at this point A. Let's do an example. And here for reference, up at the top, I have our formula for linear approximation at A from the previous slide. F of x is approximately equal to the linear function L of x, which is f of a plus f prime of a times x minus a, for values of x that are close to a. In this example, let's find the linear approximation of the function f of x equals the fifth root of x at the point a equals 32. So here's the picture. We have our function f of x equals the fifth root of x, this nonlinear function, and we're interested in the point a equals 32, right here. Now f of 32 is the fifth root of 32. It equals 2. So we have a point 32, 2 on the graph of our function, and there's a tangent line to the graph at that point, shown red here, and that tangent line is y equals L of x, the linear approximation to f of x. And notice what a good approximation L of x is to f of x for values of x that are close to 32. In fact, you can barely tell the difference between the graph of L of x and f of x near this point. And sure, for values of x that are further from 32, there's some visible deviation. But for values of x close to 32, L of x is very, very close to f of x. And here in this example, we're looking for the formula for L of x. We're going to fill out this formula by plugging in 32 equals a. And our function here is f of x equals the fifth root of x, or x to the power of 1/5. In applying the formula, notice that there's going to be a derivative, f prime of a. So the first thing we should do is compute that derivative, and we can get it with the power rule. F prime of a is 1/5 x to the power of 1/5 minus 1, which is 1/5 x to the power of minus 4/5. And cleaning that up a little bit, bringing this negative exponent down to the bottom as a x to the power of 4/5 and converting to radicals, f prime of x is 1 over 5 times the fifth root of x to the power of 4. So we're now ready to do our linear approximation. According to our formula, f of x is approximately equal to L of x, which equals f of a, that's f of 32, plus f prime of a, that's f prime of 32, times x minus a, and that's x minus 32. F of 32 is the fifth root of 32. F prime of 32, you can see here, is 1 over 5 times the fifth root of 32 to the fourth, and then times x minus 32. Continuing, the fifth root of 32, as we said before, is 2. Then we have this fraction 1 over 5 times the fifth root of 32 to the fourth. That's 1 over 5 times 2 to the fourth. 1 over 5 times 16 is 1 over 80 times the x minus 2, or x minus 32. And there we have it. We've got our linear approximation, L of x, is the simple linear function 2 plus 1 over 80 times x minus 32. So f of x is approximately equal to this simple linear function 2 plus 1 over 80 times x minus 32 for values of x that are close to 32. Now note here that f of x is the fifth root of x. It's a pretty complex function that's hard to work with, but we have it approximately equal to a very simple linear function that's easy to work with. To underscore this point, think about not the fifth root of 32, but the fifth root of 33. That's hard to work out in your head. 33 is 1 past 32. It's right there. It's not a perfect fifth power. so it's hard to work out its fifth root in your head. But notice that from the picture here, although we can't work out f of x equals the fifth root of 33 in our heads, we can work out L of 33. And that's very, very close to the fifth root of 33. So in terms of this picture, the fifth root of 33 is f of 33. And by our linear approximation, that's very close to 2 plus 1 over 80 times x minus 32. And here x is 33. So that's 1 over 80 times 33 minus 32. And that's really simple to work out. 33 minus 32 is 1, so we just get 2 plus 1 over 80. That's 160 over 80 plus 1 over 80, or 161 over 80, which works out to be 2.0125. So we see here that even though we couldn't compute the cube root of 33 in our heads, we can see that it's very close to f, or L of 33, which is this value, 2.0125. You could take a calculator and get a better approximation. With a calculator, the fifth root of 33 is, to at least 8 decimal places, 2.012346661. And notice that's very close to our approximation. In fact, our approximation, you can see, is correct to 3 decimal places. And that's pretty good. Let's move on to our next topic for today, differentials. This topic is all about making sense of the notation f prime of x equals dy dx. As you know, dy dx is an alternate notation for the derivative f prime. It's an interesting notation because it looks like a fraction, dy over dx. What we're about to do is make sense of this as a fraction. We're going to give precise meanings to the terms dx and dy. And these two things, dx and dy, are going to be called differentials. If you look at this equation, f prime of x equals dy dx, aside from the f prime, there are 3 terms. There's an x, there's a dx, and there's a dy. We know what x is. It's the value that we plug into the derivative. But what is dx? And what is dy? We're going to define them now. Given a function y equals f of x, we define 2 variables called dx and dy as follows. And here dx is just the name of a variable, and dy is the name of another variable. They're different from x and y. Dx is one variable, and dy is another variable. And we get them this way. Start with the graph of y equals f of x, and pick an x value. It's easy to say what dx is. We interpret the variable dx as simply an increment to x. It's something that you would add to x. So if x is here, x plus dx might be over here. And dx is a variable, so if dx is big, x plus dx is way over here. If dx is close to 0, x plus dx is close to x. If dx is negative, x plus dx would be over here to the left of x. So that's what dx is, simply an increment to x. What is dy? Here's how to define it. We're going to make a right triangle whose corner is right here at the point xf of x, and whose hypotenuse is aligned with the tangent line to the graph of y equals f of x at that point, as illustrated. And the horizontal side runs from x to x plus h, as we have here. So this horizontal side is the distance from x to x plus dx, so that's simply dx. we define dy to be the vertical side of this triangle. That's dy. So dx and dy are variables that equal the run and the rise of this triangle, respectively. If you look at the way this is configured, dy divided by dx is rise over run for this triangle, and that's the slope f prime of x. So dy over dx equals f prime of x. Taking that equation, dy over dx equals f prime of x, multiply both sides by dx to isolate the dy, and you get dy equals f prime of x times dx. So these two variables, dx and dy, are actually related by an equation. Dx is like an independent variable. Dy depends on dx. It's f prime of x times dx. If you change dx, you're going to change dy according to this equation. Notice what's happening here in this picture. We've defined dy to be f prime of x dx. So if we take the quotient dy divided by dx, that's f prime of x dx divided by dx, and the dx's cancel, and you just get f prime of x. So we've configured things here so that the quotient dy dx equals f prime of x, and that completely conforms to our original meaning of the notation dy dx, being the derivative f prime of x. It's important to realize here, however, that dy and dx, those are variables, and dy depends on dx. So you could change this variable dx, make it bigger or smaller, and that would force the size of this triangle to change as well. Making dx bigger makes that triangle bigger, and correspondingly makes dy bigger as well. We usually think about dx as being a fairly small quantity, or sometimes a very small quantity, so consequently dy is small as well. You think of that triangle as being very small. But the way it's set up is dx and dy. Dx could be any variable, any value that you wanted it to be, and dy is f prime of x dx. So this triangle could have all kinds of sizes. These variables, dx and dy, as defined here, are called differentials. They are related by the equation, the differential dy equals f prime of x times the differential dx from this picture. Now, notice in this equation, dy equals f prime of x dx, there are actually three variables. There's a dy, there's a dx, and also there's an x right here. It's a three-variable equation. So there's a lot going on there. As I said, we usually interpret dx as being small, so this triangle is small. And the reason we do that is that there's an interpretation that we get for small values of dx. If dx is small, think about dy. It equals the approximate change in the function y equals f of x when x is incremented by dx. So we have an x value right here. We added dx to it. dy is the vertical side of that triangle. And note that that's very close to the amount that f of x increases by when x increases from x to x plus dx. So that's a fundamental interpretation of these differentials. There's a lot going on here. We've got a three-variable equation relating dy, dx, and x. Maybe we can clarify this with an example. Let's take, for example, the function f of x equals x squared. Here we have differentials dx and dy, and as on the previous slide, they're related by the equation dy equals f prime of x times dx. F of x is x squared, so f prime of x is 2x. So this simplifies a little bit. Dy is equal to 2 times x times dx. And again, there are three variables, dy, an x, and a dx. Let's look at the situation where the variable x equals 1. If x is equal to 1, dy would be 2 times 1 times dx. In other words, dy is twice dx. It's double dx. Let's look at the picture. Here's x equals 1, and here's our triangle with a run of dx and a rise of dy. And the equation dy equals 2 times dx is just saying that the rise of this triangle is just twice what the run is, which makes sense because the slope there is f prime of 1, which is 2. So you can imagine in this picture, dx could get bigger, the triangle would get bigger. The vertical side is just twice the horizontal side. We could take different values from x other than x equals 1. How about at x equals minus 2? In the equation dy equals 2 times x dx, if we plug in x equals minus 2, we get dy equals 2 times minus 2 times dx, and that's dy equals minus 4 times dx. And let's look at the picture. We're at x equals minus 2, which is over here. And look at the tangent line. You know the tangent line is going to be f prime of minus 2. That's 2 times minus 2. The tangent line has slope minus 4. And we get the equation dy is minus 4 times dx. And that just means for a run of dx, your rise is dy, which is minus 4 times dx. So whatever dx is, your dy is minus 4 times that. So for any value of x, whether it's 1 or minus 2 or any other value, you can form these little triangles whose runs are dx and whose rises are dy, where dy is 2 times x dx. And those are your differentials dx and dy at the various values of x. To recap, today we've talked about two things. First, linear approximation, where f of x is approximated by a linear function. This is a helpful concept, but it's not something you'll use every day. The formula is not going to play a big role for us in this course. We will use it in the next lecture, but not much after that. We also talked about differentials. Given a function f of x, the differential dy is equal to f prime of x times the differential dx. And you will see some differentials in this course, but they're not going to play a really huge role. It's almost like you can ignore them, to be perfectly honest. They won't play a big role for us. However, they are very important. And their importance may sneak up on you if you take Calculus 2 and 3. There's a lot to be said about differentials. As you continue in calculus, and if you continue, new layers of meaning in differentials will emerge. And I think it's best to wait until you get to that point to explore that. We have the basics for differentials today, and that's enough to get us through Calculus 1. But don't lose sight of this idea. It'll come into its own later. That's it for today. Coming up next will be Lecture 37 on Newton's method. It's a method of solving equations that uses linear approximation, which we talked about today. And I'll see you then. Goodbye.